the derivations of the trigonometric definitions. There are 6 trig functions, and we are going to come up with or derive the formulas for all 6. And we will discuss where they get their names and why their definitions are the way that they are. So I have a circle shown here in the xy coordinate plane, and it is centered at the origin. So here's what we're going to do. I am going to introduce a radius from that center to a point on the circle in quadrant 1. And this circle is going to be a special type of circle, and we call that a unit circle. And why it is special is because when we have a unit circle, the radius length is equal to 1. So this distance is 1. And when I introduce that radius, there is an angle formed between that radius and the x-axis, and I'm going to label that angle with a Greek letter called theta. This Greek letter is going to pop up time and time again in trigonometry. What I want you to recognize is that it is a variable, and it represents an angle measure. So it's pronounced theta, and remember, it is a variable. The first thing we're going to look at is if I introduce this radius to the circle, what is a way to calculate the length of this vertical leg that I have now drawn to make this right triangle between the radius and the x-axis? We call this side the sine of theta. Okay, so it's S-I-N, but it's pronounced sine. So it is just an abbreviation, and it is accompanied by some angle measure. So the sine of theta is going to be dictated by the measure of the angle. You can imagine if I open up this angle more, the length of that vertical side is going to elongate, meaning the value of this sine is going to grow. But if I close down this angle in this direction, the length of that vertical side, which is supposed to represent sine, is going to shrink. Okay, so sine is not always the same. It's going to depend on the measure of the angle. So it's important when we write our trig function, that's going to be the case for all these trig functions, they are accompanied with some angle measurement. So now, where does sine get its name? Well, its etymology, I think, has been lost in translation or mistranslated, if I remember correctly. But one translation I have seen before is that it represents a bowstring. And if that is in fact correct, it actually makes visual sense in this case when I draw a picture like this. So imagine if I extend that line out to make a chord, a complete chord on the circle. If I look at this arc that's associated with that chord or intercepted by that chord, you can imagine that that is a bow, and then the string is the length of the chord, right? So why don't we consider the whole thing for a sine if it's supposed to be bowstring? Well, due to the symmetric nature of this circle about that axis, and knowing that the radius is running perpendicular to that chord, and we've discussed that when that happens, the chord gets bisected, it's kind of redundant to look at both halves, so you only look at one. So I think that's kind of cool that if it, in fact, it does translate to bowstring, you can kind of see like a bow and it being the string on that bow. So kind of neat. So there is what we call the sine. So what we want to know so far for our definition of sine is that sine of theta is equal to what we're going to call the opposite side when the hypotenuse of our right triangle is 1. So let's get into what we mean by opposite, hypotenuse, and another term that's going to come into play, adjacent. So if I'm looking at some acute angle theta in my right triangle, we know what the hypotenuse is. It's always going to be our longest side and the one opposite 90 degrees. But when we reference the opposite side or the adjacent side, that is always in relation to a specific angle. So if I'm talking about the opposite to theta, we're talking about the side across from theta, and the adjacent side to theta is the side right next to it. Okay, so opposite is the leg across from that angle, and adjacent is the leg next to that angle. But those are going to change if I'm now looking at the other acute angle in the right triangle, which I'll name alpha. The opposite to alpha is now that side across, so it's going to be this. So the adjacent to theta and the opposite of alpha are the same side. Okay? It is not the case that the opposite of alpha and the opposite of theta are the same. So it is all in relation to a specified acute angle in the right triangle. So that's important. So now, we know sine is opposite when the hypotenuse, so opposite to theta when the hypotenuse is 1. But here's the catch. As you can imagine, if this is our sine theta, when this is 1, we're not always guaranteed to have a hypotenuse of 1, and we should still be able to calculate the sine of an angle. So what do? Well, imagine if we scale this triangle by some factor a. So we multiply every side by a. Now the opposite side is no longer sine theta, but rather a sine theta. So how do I get my value for sine? We're going to take this opposite side, and if we divide it by the hypotenuse side length, those a values will cancel, and we'll reveal our side. So we're going to do opposite divided by hypotenuse, which is going to be a sine theta over a. And those a's cancel, and we're just left with sine theta. So in the event we don't have a hypotenuse value of 1, we're still able to calculate the sine of an angle by taking the ratio of these two side lengths. So there is our first trig definition. The sine of an angle theta is equal to the length of the opposite side divided by the length of the hypotenuse. And in fact, I'm going to abbreviate this further. We'll use O over H for opposite over hypotenuse. So there is the first of the 6. So the second one that we're going to look at is what we call the cosine. And the reason why we're doing this one next is because you see sine is present in its name. So what's the difference? Well, anytime I see co, which is going to pop up in 2 more of the 6 trig functions, we should be thinking of complement. The cosine is equal to the sine of the complement to the angle. Okay? So if we're looking for an abbreviation is going to be cos of theta, we're going to be looking for the sine of the complementary angle. And we're going to use alpha to represent our complements. So when I go back to my triangle on this circle, this is complementary to theta, alpha. And the reason we know that is because acute angles in a right triangle have to be complementary in order for the sum of the interior angles to total 180 degrees. So I know that angle is the complement to theta. And if cosine of theta is supposed to be the sine of the complement, and we know the sine is the opposite side, so I know that this is sine of alpha, well then this side should equal the cosine of theta. So if I'm trying to define cosine or all of my trig functions in terms of theta, then we could say that the cosine is supposed to be the adjacent side when the hypotenuse is equal to 1. But as we know from the sine example, the hypotenuse is not always 1, so it could be scaled. So how do I calculate cosine in the event that I have a triangle where the hypotenuse is not 1? Well, if we take the ratio of the adjacent side to the hypotenuse, these a's cancel, and we're just left with cosine of theta, and we now have a definition for cosine, which is adjacent over hypotenuse. All right, so now, this triangle that I have drawn in the circle has the hypotenuse value set equal to 1. But what if we change our triangle so that one of the legs equaled 1? And when we do that, we're going to get some new trig functions and trig definitions. So now I'm going to extend out so that the radius of 1 now represents one of the legs of my triangle. Okay, so we know that that is now a value of 1. This is our angle theta still. So what is the length of this side of the right triangle? Well, it is not going to be sine, because sine is the opposite when the hypotenuse is 1, but hypotenuse is not 1. It's greater than 1 in this case. So what is the opposite side when a leg or the adjacent side is 1? Well, you may be interested or find it interesting that this side is what we call the tangent of theta. So TAN is going to be the abbreviation. And why do you think it's called the tangent of theta? Because that side is running tangent to the circle. So pretty cool why that is the case. And another connection to the lines we introduced in the circles unit is the hypotenuse in this scenario is what we call the secant of theta, abbreviated SEC. And why do you think that side's called the secant? Because if you extend that side that represents the hypotenuse, we have just drawn a secant line. And those are two of the 6 trig functions, tangent of theta and secant of theta. And now we have to come up with definitions for them. So we say the secant of an angle is equal to the hypotenuse when the adjacent side is 1. And we say the tangent of an angle is equal to the opposite side when the adjacent is 1. So let's set this thing up. We know the adjacent's not always going to be 1, so we're kind of just repeating the same idea here. So we scale all the sides by some factor a. So how do I get my tangent back? Well, if I take that opposite side and divide it by the adjacent side, we just came up with a definition for tangent, given any side lengths. It's going to be opposite over adjacent. What about the secant? Well, if I take the hypotenuse and divide it by the adjacent, we'll get those constant values a, or that scale factor a, to cancel, and that will get us our secant back. So secant is going to be hypotenuse over adjacent. All right, so what 2 trig functions are missing? Well, one that is missing is what we call the cotangent. And as you can probably guess, the cotangent of an angle theta should be equal to the tangent of the complement to theta, which again we're going to use as alpha, where alpha equals the complement to theta, theta. So if we know, we have some scenario here. We have theta, we know this is alpha, that would be the complement to it. Let's call this side of the triangle x and this side of the triangle y. We know the tangent of alpha from our definition that we just derived should be x over y. This is tangent of alpha. And the tangent of alpha from its name should be equal to the cotangent of theta. And cotangent is going to be abbreviated as COT. So we're saying that the cotangent is x over y. And what do those sides represent in relation to theta? Well, x is the adjacent to theta, and y is the opposite to theta. So therefore, we can define cotangent now in terms of opposite, adjacent, and hypotenuse to stay consistent with the other ones. And we'll say the cotangent is adjacent over opposite as a result of this process. And what is the last one? The last trig function is what we call cosecant. Cosecant of an angle theta, as you can expect, is going to be the secant of the complement. So when we draw our triangle, we have theta. We have secant of theta. I'm going to label x, y, and z now. We know that secant, from our definition that we derived from earlier, is hypotenuse over adjacent. Now, we're talking about the secant for the complement to theta in order to find the cosecant definition. So we're going to introduce alpha, knowing that that is our complement. So if I want the secant of alpha, we're going to do the adjacent side to that, which is y, over the hypotenuse side, which is z. Sorry, the hypotenuse z over the adjacent y. This should be equal to the cosecant, which is going to be abbreviated as CSC of theta from its name. Now, what does z and y represent in relation to theta so that we can define a cosecant for an angle theta? Well, the z is the hypotenuse, and the y in relation to theta is the opposite. So now we have a definition for cosecant. CSC of theta is equal to hypotenuse over opposite. And there are the definitions for the 6 trigonometric functions, where they came from, and why they are named the way that they are. Now, you may be wondering why I was formatting them in this structure. And the reason is, you'll notice a relationship between the trig functions that are horizontally aligned. For instance, sine is opposite over adjacent, and cosecant is hypotenuse over opposite. Cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. And tangent is opposite over adjacent, and cotangent is adjacent over opposite. And what we have been able to find out from this is that there is a relationship between the sine and the cosecant of an angle. They are just reciprocals of one another. Cosine and secant are reciprocals of one another. Tangent and cotangent of an angle are reciprocals of one another. So you'll typically see them formatted in this structure as a way to remind yourself that those horizontal alignments indicate a reciprocal relationship. And it can make for quick and easy calculations if you have one and need the other, for instance. So there are the 6 trig definitions, where they came from, where they got their names. And in another video, we're going to look at how we use these trig definitions to calculate angle measures or missing side lengths.